Uh-oh. Hold up. Doesn't seem like our camera is active. Frozen. Let's see. All right, now we're back. All right, we were frozen there for a minute. All right, so today we are going to do some centroids. So those, well, we've been doing trusses. We did method of joints one day. We did method of sections the next day, yesterday actually, no, that was Monday, wasn't it? Monday was method of sections. And today we're going to do centroids. So they're not really related directly to trusses, but they're related direct or put to the larger topic of strength of materials. So what we're talking about when we say centroid is, the word kind of sounds like center, and it is related to the center. In some cases, it might be the center of mass, not always, but in our cases, it would be the center of mass. But we're really talking about centroids of a planar area, so like a flat 2D shape, and we need to know the centroid of that area. So that's our general goal for today, is get through some centroids. Oh, we got 5 votes. Hey, nobody's on the really bad side of been better. So our question was, how is everybody doing today? So we've got at least one person with great. That's good, or I guess that's great. Centroids. Let's go over to our. Let's see. Where are we at? Here. There we go. Go over here. And like I said, let's do a little intro to centroids and then a little bit about how they work. We'll actually use them sometime later, maybe next week. We do have an exam coming up, so I guess we'll use them on the next class. And then this is the last topic. Centroids is the last topic that is included in exam 1. So all of the stuff from the beginning up until the stuff about centroids is all mixed in for exam 1. All right, so centroids. So I'm going to start with a little bit of like a derivation of how we might think about centroids. And so this is going to be a little bit abstract for a while, and then we'll move into more of the application of, or practically, what do we do with centroids. So let's draw us a coordinate system here for what we're going to do. So that will be our x, and then, oh, why is it doing that? There we go. Let's do our y-axis. Okay. So there's a random x and y axis out here. Not super important what it's doing. It's just for reference points. So let's pretend that we have a 2D shape. All right. I'm just going to put a kind of common beam anyway profile. We'll get a lot more into these beams later in the quarter, but for now, let's just know that a lot of beams that might be in a building or a bridge or some kind of metal construction might be shaped like a T, and we'd call them a T-beam. And so we need to know the centroid of this T-beam. So again, right now we're just thinking about it kind of abstractly. So don't worry too much about what we're doing here, other than to try and get the concept of what centroids are. So we could take this beam and divide it into lots of little pieces. Okay, so I've made it into a bunch of little squares. And we can make those squares super tiny, right? We can make them however small we wanted to if we use calculus methods. Right now, we're thinking of discrete stuff, but with the idea that, hey, if I can divide it into some squares, then I can divide it into a bunch of squares or shapes. It doesn't have to be squares particularly. But let's just pick a couple of these for now, because I don't want to write, I'm going to write some equations, and I don't want to write How many did I draw there? There's 7, 8, 9, 10, 11, 12 squares or whatever there are. I don't want to write 12 values. So let's just pick a couple of these. So maybe that one, and let's pick that one, and that one. I am completely random on the ones I'm picking here. So no rhyme or reason to these other than I picked 3 of them. It doesn't even matter that I picked 3. This is just an abstract example. So each one of these pieces, whatever I want to represent them as, has its own weight, right? If it's a piece of a T-beam, then each one of these has a weight. So I'm just putting a weight at the center of each of these little squares, and I'm just showing it pointing down. That's also a little bit arbitrary for what I'm doing, but that's what I'm doing. Each one of these weights is a certain distance from the x-axis and a certain distance from the y-axis. For now, I'm going to just look at the y. So I would say that that is the distance from element 1 in the x direction, so I might call that x1. So it's like the x coordinate of that little green box 1. Here I've got 1 also. Might call that one x2, and this one I would call x3. So no matter how many of these I create, they each have some distance from the y-axis. And they also have a distance from the x-axis. Just my diagram gets really cluttery if I draw all of those on there also. But you could imagine that they would be similar, just measuring vertically from the x-axis to the center of each of these little rectangles or squares. Okay, so what I want to do is I want to find the centroid of this entire shape. So I can imagine that the centroid of each of these little elements is right in the center of it, because I can make them super tiny, like to where they're just a dot, or smaller. And so the centroid of a dot is the dot, So if I could make a whole bunch of those and do this process. But what I want to know is this whole shape, this T shape, it has its own centroid as like a T-shaped thing. And I'm going to just say that is somewhere, I don't know exactly, but maybe it's right here. So that, we will say, is the location of the centroid for the T-shape. And all the little dots here, those are the individual centroids of all of my little green pieces, no matter how small I make them. And I only drew 3 of them because it gets even more cluttery if I try to draw all of them. All right, so this centroid, if I follow the same naming convention I've been using, I would just call it x sub c. So x sub c is the location, or the x coordinate, let's put it that way, the x coordinate of the centroid of the T shape. And so this would work no matter if it was a T or a C or a blob or whatever, same idea. Okay. Oh, we got some more votes. We're still doing okay, I think. 7 votes. That's good. All right. Also, that the centroid thing, the red one, I guess all the centroids I drew were red, but the one with the X in the middle. If I were to take the weight of the entire T, that would be where its weight would be. So I put weight T. That could be either because it's a T shape, or it could be like the total weight, whichever way you want to think about it. Okay, now let's write a little random equation. Not random, but I guess abstract a little bit. We're still thinking of this as a method that we can use and apply to a whole bunch of stuff. So WT, the total weight of the centroid, would equal all of my individuals however many of those little elements I made, if I add up all their individual weights, I'm talking about like this one and this one and this one. If I added all of those together, they would equal WT, the total weight. Okay, that seems pretty ordinary. I'm keeping an eye on the chat in case anybody has questions. So we could write that as the summation of W sub I. So however many of these little green elements I have, just add them all up, add their weights all up, and that's the total weight. Okay? I could also say that if we think about that idea of moments that we introduced a while back, where if I have a weight or a force and it's some distance away from something, then it creates a moment, right? Now, I'm having to be a little bit more abstract here because I'm talking about a 2D shape, but this 2D shape represents like a beam. So this 2D shape would represent a beam that might look like this in 3D. Something like that. So there's the little T, and it extends out and makes a long beam that has a T-shaped cross section. So this T-shape represents that whole beam, which does have a weight, but we're thinking of just a single cross-sectional T-shape that's really just 2 dimensions. All right. So each of these little individual weights could create a moment about an axis. Now, I'm in a 2D plane here, and the moment might get a little confusing, but you can at least see for like W1, it is X1 units away from the Y-axis. So I've got a force or a weight, and it's some distance away from an axis, so that reminds me of a moment. And I could say something like W1 times X1 is that moment, and I can add up all of these things. So all of those added, however many I create, however tiny they are all some distance away from the y-axis. Maybe some of them are actually on the y-axis and they have no moment arm, but that's okay. I could add them all up. And they would have the same, if I did add all of them together, they would have the same effect, or they'd be equal to, in my equation, I'm going to use equals, they would be equal to the total weight times wherever that centroid is. That guy, X sub C, the one I drew in red. I could also write this equation in the same form that I wrote before. I could say that, let's see, we'll just indent. WT times X sub C equals the summation, because I'm adding up all of these individual little green boxes, not blockses. WI times X sub I. Okay? Now, I've got 2 equations here that I've written out. I've got the one I just wrote, and I've got the WT equals summation of WI that I wrote previously. I've got, there it is, and I've got that one. So both of these have WT in them. So I could take this value and plug it in for WT, and then I have a new equation. I have, we might have to get some more room on our page. I have summation of W sub I times x sub c equals summation of wi times xi. Okay, and I could then isolate x sub c, and I have an equation for finding that value for x sub c. X sub c equals the summation of wi times x sub I over summation of wi. So a couple of these things have special names. Well, actually not quite yet. We've got a couple of simplifications to make, and then we'll get to that. So that x sub c, remember, that is, I wrote it up here, that's the x coordinate of the centroid, right, whoops, didn't want to do that, right here, that's the x coordinate of the centroid of the T shape, and I have an equation for it now. There's an equation that tells me. I could write a similar one if I changed all the x's to y's and then measured from the x-axis up to the center of each one of these little green elements. I'd get a similar equation, and it would say y sub c equals summation of wi times yi over summation of wi. So I could get both of those equations. We can simplify them a little bit because we know that we're talking about things like this T-beam over here. So we're talking in general. Now, if I'm not talking about a beam that has these certain characteristics we're about to talk about, then maybe I can't simplify it in this way and I have to do something else. But for this course, we're going to say that these simplifications that we're about to do are true. So one of them is that weight equals mass times g sub c, which is weight is proportional to mass. We're assuming that g sub c, the gravitational constant, does not change from one end of a T-beam to the other end of the T-beam. We're not making like space elevators or something like that. We're making a skyscraper maybe, but for all practical purposes, the acceleration due to gravity doesn't change from one piece of this beam to the other piece of end of this beam. So we can pretty safely say that. We also know that density is equal to mass over volume. And so we can write an equation, density, rho, equals mass over volume would be this cross-sectional area. So like if I shaded in all of this, that's the cross-sectional area of that T. So I'm just going to call that A. Cross-sectional area. So that's this A right here times however thick this beam is. And in thickness, I mean this dimension here. How long is the beam? Could have used an L, I suppose. Okay. So in this case, I'm going to say that for the most part, this is rho. That's my Greek letter rho, and I'm using it for density. For engineering materials, density doesn't really change from one piece of the material to the other piece of the material. Now, you can have different materials with different densities, but density does not change from, and I'm using this particularly in the context of beams, which we'll get to after exam 1. Density does not change from one end of a beam to the other end. So it's constant. Also, the thickness here, this thickness here, the T, now my drawing may not be that great, but the T shape doesn't really change from one end of the beam to the other end of the beam. So the thickness of it is, it's not really relevant, other than it helps me create the volume. It's not like one end of this beam is a T, and then as it goes down the beam, it becomes a circle at the other end. You know, it stays a T and pretty much the same size T from one end to the other. Now there are like conical shaped beams and things like that that we might have to deal with. So this little simplification may not always apply, but for this course it does apply. So beams tend to not change shape, or cross-sectional shape, from one end to the other. They can, but that's not what we're talking about. Okay, so what these simplifications, the idea that weight is mass times G sub C, and G sub C is constant in most engineering settings. You know, one beam pretty much experiences just one value for G sub C. Weight is proportional. Oh, this little symbol right here means proportional. Weight is proportional to mass if gravity doesn't change in that scenario. Density is mass over volume. So I rewrote that equation in variables. And what all of this tells us, that density is constant, the thickness doesn't really, the cross-section doesn't change along the thickness, it's not a function of the thickness, then I could say that area is proportional to mass. And we could have just said that, all right? We could have just, that's pretty intuitive, that the bigger the thing is, the more mass there is. But it's not always true unless you make all these little assumptions that the density doesn't change, because you know, we could maybe at one end of the beam it's area, but it has the density of styrofoam, but the other end of the beam has the same area but the density of steel. Then yeah, the mass did change, or well, the weight did change. And so we can't always just say that without having all these gravity's constants, density's constant, the cross-sectional area doesn't change from one end to the other. All of those statements have to be in place for us to say that, yeah, area is proportional to mass, and mass is proportional to weight, and all of this stuff. So what I can do with that, and the whole point of this little thought process, is that I had equations here that were in terms of weight, right? Both of those equations are in terms of weight and this x sub I, y sub I thing. But the x and y's are just distances. That's relatively easy to deal with. But if area is proportional to mass, mass is proportional to weight, then I can replace this weight in here with area. So that's my whole point. X sub C is a little bit easier to deal with if I say the summation of A sub I times X sub I over the total area. So the denominator before was summation of all the weights, but area is proportional to mass, mass is proportional to weight, and so I'm just going to, instead of summing up the weights, I'm going to sum up the areas. Okay, same thing with y sub c. Summation of A sub I times y sub I over the total area. So this is a discrete method, and this is what we'll use most of the time. But you could end up with a shape that's doesn't lend itself to discrete processes very easily. We need continuous processes. So we could also say, instead of discrete summations, we could say that x sub c equals the integral of x times dA over integral of dA, which would just be the total area. We could do the same thing for y sub c. Y, or y, not yi, just y, times dA, didn't do the integral sign, over the integral of dA. So sometimes we'll do one problem where we use the integration just so you can see how it works. Most of the time, though, we're going to use the discrete, the summations. There is a special term here. This numerator, this is called the first moment of area. So that's kind of a weird combination. First, because the y or the x, whichever one I'm talking about, has an exponent of 1, right? You know, there's only 1 here. There is a second moment of area that we'll do later. It is a moment because way back here, when we started doing this, we were kind of summing moments here. We had a weight times the distance. So that's the moment part. And then of area, because we went through this process where area is proportional to mass, and I guess I never wrote it, but from this previous one, mass is proportional to weight. And so instead of dealing with the weight or the mass, we're dealing directly with the area. Okay, so these 4 are our important equations. We'll make them something like that. All right, so let's use these equations. First, let's use the integral version. Now, to simplify our use of the integral, you could do this by hand. I'm going to jump over to MathCAD. I think I have it open. Going to jump over here to MathCAD so that we can let it do the integration for us. On the exam, I'm trying to think. I don't even think we have to do an integration process by hand on an exam. But if you do, it would be one where the integrals are actually pretty simple to calculate, or I would give you a reference sheet that has, you know, this integral equals this equation. All right, so let's come up with a relatively simple shape that we want to deal with. So let's just use a parabola. Y of x equals 3x squared plus 9. Oh, no, let's not put that in the numerator though. Plus 9. Okay, and then let's plot that. So let's do, where's plot at? Plot, insert plot right here. Insert an XY plot. Y of x on the there and x there. So there's our parabola. Let's only go from 0 to, well, let's go into 10. So that's good. So what this would be, let's copy this. This is not a common shape for a beam, but if we were using this, then the beam cross section would actually be this. And all of that shaded in. So I guess if I'd have to close it off, wouldn't I? Well, I didn't want to move that. That's not, I wanted a straight line. Didn't get a very straight line there. Okay, so our beam would be a little bit weird. It'd be something like, I don't even know if I can draw this thing. You know, something like that would be our beam if this was its cross section. So the area under the curve would be the shape that we're dealing with. So there might be some situation where you've got a I don't know, deal with a teardrop shape or whatever, and you've got these curves that define the boundary. Now here we've got one curve, and we're just talking about the area under that curve from 0 to 10, whatever these units are. That's what we're trying to find the centroid of. So in our mind, we can kind of visualize, well, the centroid's somewhere over here, you know, something like that, 7.5 or so for x. Okay, and it would have a y sub c also. We're just going to do one of them to make it relatively simple. The same process would work for the y sub c, the y coordinate of that centroid. So we need to apply this equation at the top of the screen. X sub c equals the integral of x times dA over the integral of dA. So the integral of dA in the denominator is just the area under the curve. It is this area. So we'll throw that into MathCAD here in a second, and it'll tell us that area. But the numerator is a little bit different. It has that, but it's also x times that. So how that works is you need to imagine, this is what the calculus part is doing for you. Imagine that you have this little integral strip, maybe there, and it has, you know, it's shaded in, and you have a whole bunch of these, right? Let's put another one right beside it, going up to there, and then there's another one right beside that. Okay, there's a whole bunch of these little strips, kind of like there were a whole bunch of little rectangles over here. So you've got a whole bunch of these. Each one, the area, so like this green area, that is dA. And I could write an equation for dA. So dA equals the height of that green column, which is just y of x. So the equation itself determines the height of it, times the width of it, which the width is this width right here. And that width is dx. Right? So now my equation is integral of x, so x is part of the equation, times dA, but I've decided that dA equals y of x times dx. Okay? And that's my new numerator. Let's try to plug these in to MathCAD and see if it will give us a value for our x centroid. Let me, before we go to MathCAD, let me make sure we understand what the x is. So x is just like it was up here, x1, x2, x3. It's the distance from my little element, the little green element, to my reference axis. In this case, I'm doing the y-axis because I want to measure in the x direction. So x is from the center of my strip here, my element, over to my reference axis, which I've got x equals 0, I guess, the y-axis at x equals 0. That is x. That's that x. Okay? So that's just going to be a variable that goes from x equals 0 to, I've got it set right now to x equals 10. So that's going to be my limits of integration on my integral, however wide this beam is. All right, now let's go to MathCAD and see if we can get this thing to do what we want it to do. All right, so there's kind of our graph of our top surface anyway. Remember over here, I drew in the other edges of my beam so that it was a solid shape. But I'm just talking about the area under this curve. So I want to write the equation integral of x dA over integral of dA, except I've got dA set as y dx. So I actually want the integral, Control Shift I is integral in this version. I'm going to go from 0 to 10. And I just picked those numbers myself. We could have, made it whatever we wanted. I'm going to integrate not over dA, because I have set dA equal to y dx. So I'm actually going to integrate over dx. So dx, and then I'm going to integrate x times y of x dx. Okay, that's my numerator. That's just a thing I can evaluate. It's this giant number. Okay, and I could put units on here. It wouldn't really change anything, but I could have 10 inches or whatever, centimeters or whatever these units are. It would just have units on it. That's the numerator. So of this equation, that's the numerator. Now I need to divide it by integral of dA. That was left over from this step right here, where we divided out the total weight so that we could isolate x sub c, because that's what we really want to know, is where is the centroid. So I want to know this x sub c. So let's find integral of dA over here in MathCAD. So that would be Control Shift I. We're going to still integrate from 0 to 10. We're going to integrate over x, and then we're going to integrate y of x. So basically we're just integrating this function from 0 to 10. Okay? And it's a smaller number than it was, this other one was, because this other one was multiplied times x. And then let's make it finally what we want. X sub c is equal to Control Shift I from 0. I'm just writing it over again. 10 x times y of x dx. All of that. Whoops, not all of that. All of that over integral 0 to 10 y of x dx. And all right, let's just, before we solve this, I haven't actually solved this one, so I made up I've done it before with different limits, from 0 to 3 or whatever, so this is a little bit different. We thought, looking at our diagram, remember the centroid, as long as all of that stuff was true about the density and gravitational constant, and our beam doesn't change area from one end to the other, if all that's true, then the intuitive part of this would be that I could cut out this shape, this little weird parabola type shape. I could cut it out, and the centroid is where, if I laid it flat, it would balance on that point. So we looked at it, and we kind of just roughly drew the centroid in kind of right here, and on our graph that looks like it's supposed to be about 7.5. So that's a good way to check if our math is anywhere near right. 7.3, I'm okay that I thought it was 7.5, 7.3, that's close enough. We probably did everything right. So we would do the same thing, except with the y coordinates, if we wanted to know y sub c. So same idea. Now, fortunately, we don't have to do this too often. This is just so that we have an intuition about what's happening, because what we most often do is use these discrete equations. Okay, so let's do the same thing. Well, not with the curvy line parabola. Let's do a t and show how that would work. All right, so let's put, we do need reference axes, so I'm going to put an x-axis and I'm going to put a y-axis. And then let's make a T-shape in here. I don't know, let's put it right here. And just for fun, let's make the stem of the T, really thick. Usually not like this, but that's what we're going to do. Let's put some dimensions on it so that we have numbers we can work with. And let's just use our coordinate system, our grid system here. This will be 3 units. This will be 1, 2, 3, 4, 5, 6, 7, 8. That'll be 1. And that's all. Oh, we need this one. 1, 2, 3, 4, 5, 6, 7, 8, 9, I think. Nine. Okay. So this is our T profile for a beam similar to this one over here, although we made the stem of it, the vertical part, thicker than they normally are, just so we have different numbers to work with. All right. And it probably doesn't have this little set of lines right here. You know, it's all one thing. Okay, so I'm going to show you what I call bookkeeping method for how we can do this. Now, what we're wanting to solve are these equations right here. Where'd they go? Wow, I don't know why it's doing that all of a sudden. We want to solve these equations right here. And so what we need to do is we need to calculate this numerator and calculate this denominator, and that will tell us, when we do the math, the value for x sub c and the value of y sub c. So in our bookkeeping method, I'll put it over to the side here. Let me make sure, right there. We've got to divide our T shape into primitive shapes. So the easiest way is to have shape 1 be a skinny rectangle horizontal, and shape 2 be a kind of fat rectangle vertical. So what I would do is, in my bookkeeping, I have part 1 and it's a little rectangle. Part 2 is that rectangle. Okay. In these equations, why don't we copy our equation here and kind of keep it handy. We also need the y equation because we're going to do both x and y. Okay, so in our equations, they all have these areas. So actually, let's get a little more room in here so it's not so crowded. So I'm going to put 2 down here. Okay, so that's the parts I'm dealing with, and there can be as many parts as I want to deal with. This one just needs 2. Next column is going to be area. It's going to have units of, let's just say everything is inches. So this will be inches squared. And I go to my calculator, which I have again lost. It was here earlier, and now I don't see it again. Got my phone. Guess we can do that. I do have MathCAD out there. I guess I could use it if I needed to. The first area is pretty simple, 9 times 1, so that's 9 square inches. The second area is 8 times 3, 24. And so I would keep adding up, or keep calculating all the areas of my parts. We'll do one that's got more complicated geometry in a minute, once we get our procedure down. So this is easy enough. The total area is 9 plus 24, 33. So that is what I will put in my denominators, because that's the total area. It is possible to have negative area, like I've got a hole in something, so I have to cut away area. So I could have negative. We'll try to do that on the next problem so that we have example of that. Okay. Another thing I need in my numerator is I need to multiply the area times x, or the area times y. Okay. So I need to know x and y. So x sub I is just going to be in inches. This is the distance from the centroid of my individual little pieces to my reference axis. So I've got, what I usually do is I usually draw in where the centroid is of each part. So these are rectangles, And I know that the centroid of a rectangle is right in its center. So that's easy enough. So this distance, if I just measure, is 1, 2, 3, 4, 5, 6, 7.5 inches. And this distance is also 7.5. Okay, so if I write in x sub I for part 1, I write in it's 7.5 inches from my reference axis. Part 2, also 7.5 inches from my reference axis. To complete the numerator for the x sub c equation, I have to multiply a times I. So a times, or not a times I, a times x. A times x, the units would be inches cubed. It's not a volume, but that's just when you multiply inches squared times inches, you get inches cubed. This is where a calculator would be a little more handy, and I still haven't spotted it. I know it's here somewhere, though. I'm just not sure where I put it. I really need to not lose those things. All right, we're going to do phone calculator. All right, so we've got 9 times 7.5. 67.5. 24 times 7.5. 180. If I add this column, it's almost under my picture there, isn't it? So let me scroll it down. There we go. If I add this column, then that will be the summation of a times x. So 180 plus 67.5 is 247.5 inches cubed. Following my x sub c equation, I have, let me get them, I think I can get them all on there, yes. I have the numerator, summation of a times I, is equal to 247.5 inches cubed. The denominator is 33 square inches. So if I do that math, I get that x sub c equals 7.5 inches. Now, I kind of already knew that because if I look at my diagram, all of the centroids for the two pieces, there are only two. So both of the centroids for my pieces are lined up at 7.5 inches. So the centroid of the whole shape has to be at 7.5. If all the other centroids are at some common number, then the centroid of the whole shape is at that same number. In fact, I could try, I'm going to guess the centroid for this thing is pretty much maybe right there. I'll draw a really big circle to make it different from the centroid of the part 2. And yeah, it's lined up. This distance is 7.5 inches. Okay, so that's pretty ordinary. Let's do y sub c. So for y sub c, I need these distances. So that distance is 4 because it's half of 8. The stubby thick rectangle is 8 inches tall, so its centroid is at 4 inches. This one, all right, so think about this one while I get some water. And in your mind, think of what this one should be, and then I'll write it down. All right, so the key is that you have to measure from your reference axis. So I have drawn the x-axis down here at the bottom, y-axis over to the left. So I have to measure all the way from 0 to 8, and then I add in this little bit here, so that's another half. So this is actually 8.5. All right. So if I put my values in the columns, let's see. I will, I'm trying to figure out where to put them. I've kind of I'm going to put them right here. I think that's under this. There we go. We'll put them here. So we've got y sub I for each part. For part 1, I've got 8.5. For part 2, I've got 4. And then I've got to multiply a times y. Getting a little crowded because I'm running out of screen. Actually, it's off of your screen. So let me move this stuff over a little bit so it's not off your screen. Let's see there. It's going to be really close, but now it's on your screen. All right. A times y. So I've got a of 9. Got to get my calculator going again. So 9 for area times 8.5 is 76.5. Area of 24 times a value or a y value of 4 is 96. We need to add both of those together. So 96 plus 76.5 is 172.5. And then I can go to my y equation. Y sub c, the numerator is 172.5 inches cubed. The denominator is the same as it was before, 33 inches squared. And if I do the math, I get 5.23 inches. And that's roughly where I drew it, you know. So it's always good in my mind to kind of estimate, like on your drawing, if you draw it to scale. So I did mine to scale because I use this grid pattern. If you draw your drawings to scale, then if you try to estimate in where the centroid is, assuming you're relatively close on your estimation, it kind of helps you check that, yeah, I put that at 5, a little over 5. So 5.23 sounds right. You know, it's a lot easier on the X in this case because you know that 7.5 is right. Here you have to kind of estimate that, yeah, that seems reasonable. If I'd gotten 0.5, then that doesn't seem reasonable. If I've gotten 52.3, that doesn't seem reasonable. So it is helpful to try and draw your diagrams to scale so that they so that you can use them to help you tell if you're right or not. All right, so that would, if we finish out our drawing here, that would just show, where can I put that? That would be this distance right here. It's 5.23 inches. Okay. Oh, there's a question. What if it's a weird shape and you can't... Okay, so yes. What if it's a weird shape and you can't guess where the centroid is? So the good part about that is, so if it's a really weird shape, then you're probably doing this, right? So you're probably having to figure out equations for that determine the boundary of it, and you're having to do the integral method. You're not going to have to do that in our course, but if it was something in the real world and, you know, somebody designed some really odd shaped beam, or it's an airfoil or some weird thing like that, then you're probably doing this method. But if it's a weird shape, but it's still made up of common shapes like circles and squares and triangles, then that is the perfect chance to go here. There, I've got on here, I've got it just labeled centroids. There are reference sheets like this one that give you, this is from your book for the class, that give you the location of common, but you know, not crazy, but there's a ellipse, there's a half circle, quarter circle, sector of a circle. There's even a rectangle that we've been using. There's some triangles and spandrels over here. So some odd shapes where you don't know exactly, until you start memorizing all this stuff, you don't know where the centroid's at. So there are reference tables like this, and that's what we're actually going to use in our next problem, because you don't always remember where all of the centroids are for these common shapes. Do be careful with these charts. This side over here, these three that aren't shaded in, These are just like you have a wire that's bent into an arc shape. And so that's different from like a solid pizza slice like this one, you know, or a quarter of a pizza or half of a pizza. That's different. This is just like the crust. That's all it is. So we rarely ever use these three that aren't shaded in this course, and we don't really use these three-dimensional ones in this course, but they do exist. All right, so let's use one where we need to have this reference, kind of reference stuff. So we've been using rectangles, and I didn't even point it out, but they are in the charts also. You can see one here where it just says, oh, a rectangle, x sub c is in b over 2, b is the base, so it's right in the center. But let's make a new shape that has non-rectangles, or maybe just not only rectangles. All right, so this one, let's see, I had a shape picked out I wanted to do. Oh yeah, here it is. All right, so let's say we've got this there. Let's see, let's make it a circle. We'll have to erase some of that one, but we'll get to that in a minute. I think there, maybe? And then let's erase this part. All right, so we have a realistic shape. You know, maybe it's not a beam, but there might be some plate that you've got to weld stuff onto, or it's a bracket or something like that, and you need to know the centroid of this thing for some calculations you want to do later. It's not just rectangles. So how I would do this one is I would still think about rectangles first. So what I would do is I would think that it was originally a rectangle, and then it's had these shapes chopped off of it. Right? So it was originally a rectangle that is this dimension. Actually, let's go down here. What is this? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13 by whatever this is. 1, 2, 3, 4, 7. And then this is 3. This radius is 3. This distance is 4. So is this one, I'm just using the grid to determine the distances here of everything. I think that's all we need, right? Okay, everything else is, we do have some things that are not labeled, but everything else is determined by dimensions that we have on here, I think. All right, so this one I would say we would treat as 3 parts. The rectangle, and then the quarter circle that we've cut away, and then the triangle that we've cut away. Oh, we need a reference axis. We do need that. Because it matters where we put our reference axis. Now, if I choose, then I'm probably going to put the reference axis in the bottom left corner. But on a homework or an exam, the reference axis is already on the problem statement, and you just have to deal with that one wherever it's at. So let's just say that I choose the reference axis, and I want to put it, let's put it right here. There's a reason I want to put it over here, but normally I would put it in the bottom left corner, but let's say that Y is there and X is at the bottom. Okay, again, normally I'd put the reference over here, but we're not going to do that for academic purposes. All right, so let's make our chart. Oh, let's keep that dimension up there. It doesn't want to scroll exactly where I want it. We'll deal with that later. All right, so we have parts. Part 1 is the rectangle. Part 2, I'm going to draw this one kind of dotted line to remind me that it's a cutout piece. And part 3 is another cutout piece. You don't have to be particularly fancy with your part drawings. You don't even have to draw them. Once you get familiar with this, you can just use the equation. You know, you can just solve this equation, either of these. Okay. All right. So let's estimate where our part is, our centroid for each of our parts is. For the rectangle, it's going to be right in the middle. For the triangle, remember, it's as if I cut out this triangle and I wanted to balance it. So I don't know, somewhere over there. And then the quarter circle somewhere over there. Those are our individual ones, just so that we have a rough idea of where they're going to be. And then the whole part, it's kind of hard to guess. But I'm going to guess it's a little bit to the left and a little bit, I actually don't know, maybe right in the middle. So maybe the whole centroid is somewhere right there. I don't really know. But in that vicinity. It might be further to, you know, that right corner, though. It looks like there's more material over there. So, but it's fine. We know it should be somewhere in the middle-ish. All right, let's do our areas. Again, I didn't put units. Let's just assume they're inches. I got to get my calculator again. I really should. I keep thinking I'll see that calculator somewhere, and I just don't. Oh, wait. Nope. All right, well, this will work. We just have to multiply and add and stuff like that. So we'll use this. All right. So the area of the rectangle, 13 by 7. It's the area of the rectangle, not the cutaway stuff. So the whole rectangle, 13 by 7. In fact, I'll write 13 by 7 equals 91. Okay. The area of part 2 is a fourth of a circle. So pi... I have the radius, so pi r squared, so 3 squared, but it's over 4 because it's only a fourth of a circle, and it's negative because I cut it away from that rectangle, the 91 square inch rectangle. So 3 times 3 times, this does not have pi on it, 3.14159 divided by 4, negative 7.07, we'll say. I did round a little bit there, so if you're solving these in web work, some of that rounding might add up to where it doesn't work. Our triangle is also negative, and it is 3 times that length there is 9, but it's a triangle, so divided by 2. That's negative 3 times 9 divided by 2 is 13.5. So our total area is equal to 91 minus 7.07 minus 13.5. 70.43. If any of you are following along and I got the wrong number, just put it in the chat so I can fix it. It's totally possible I write the wrong thing down. Okay. Now let's do, for this one, let's do both x and y coordinates for our centroid. So let's do x. X is going to be measured from the y-axis. So part 1, the rectangle, that centroid is 13 over 2. So that's 6.5. Oh, no. I better see, I'm about to mess up. Part 1 centroid is right here. I put this axis is 4 units, I guess inches, from the left side of the thing. So that's going to complicate matters, isn't it? So that distance is actually 13 and a half, or no, 13 divided by 2 minus 4. Okay, 13 divided by 2, but I subtract off 4 because of where I put the y-axis. So this distance is just 2.5. And that's what it looks like on my picture, so that makes me happy. Okay. Part 2. All right, this is one of the ones where you probably don't remember that the centroid location for a quarter circle is something like 4r over 3 pi or something like that. So let's go and check our little chart. I was right, but I wasn't sure. Here's our diagram. And let me zoom in so that we get a better... Can I move that around? No. Well, it's on your screen. All right, so 4r, so it shows x sub c measured from like the corner part of the quarter circle, and it gives me an equation. 4r over 3 pi is how far that distance is. So I do have to be careful with this, because that's not the number I need, but it's part of the number I need. So I'm going to take this, actually, I want to take this thing. It's crooked, but we're going to take this and we're going to go back over here. And we're going to move it where you can see it right there. All right, so taking that information, and this value right here is equal to 4r over 3 pi. But on my graph, or my diagram, that's that distance. I need the distance from the centroid to the y-axis, which is that distance. And I drew that arrow with only one arrowhead because I'm measuring in the negative x direction. So when I go to put this value in my chart down here, it's a negative direction, negative distance, because I had to go to the left of the y-axis. So I want 4 minus 4 times the radius over 3 pi. I want that. Now I've lost my phone. Oh, here it is. So let's see if we can do all that. 4 times 3 equals, divided by 3 times pi, 4. All right, so that's 1.27. 4 minus 1.27. So I want 2.73, but I want negative 2.73. So that negative 2.73 is that distance. And that's why I put the y-axis in this weird spot, so that we would have some practice with, it is possible to have a negative distance on our x or y values. All right, let's do our last one. We want that distance. So that is a triangle. So we need to go to our sheet here, and really, let's download this so I can open it. Here we go. There's a triangle up there. Let's get that triangle. Take it back over here. Make it a little larger. All right, so same thing with the triangle. They are measuring x sub c as this distance. So for me, that would actually that's what we need. In this case, that is what we need, because that would be from the point of the triangle, which is lined up with my y-axis, to right there, which is exactly what I need. Sometimes you get lucky. So that distance, it says x sub c is 2b over 3, so 2/3 of the base. My base is the long flat side of the triangle, which for me is 9. That distance Am I on the screen? Yeah, that distance is 9. And so 2/3 of 9 is 6. So this distance will be 6. Well, so will that one. And that's a positive 6. So that was not too bad. All right, let's move our reference triangle out of the way for now. And let's do a times x. We could do the y's, but let's go ahead and find the a times x. Okay, 91 is our area. Times x of 2.5 is 227.5. Negative is our area is, oh wait, hold on, clear. Negative 7.07 times negative 2.73 is a positive negative area times a negative distance. This is the quarter circle that is cut away and on the left side of my y-axis. So it ends up a positive a times x, 19.3. The triangle has a negative area, 13.5, but a positive x location times 6, so that gives me a negative 81. Now if I add all this together, 227.5 plus 19.3 minus 81, 165.8. So that would be a times x equals 165, or the summation of a times x, 165.8 inches cubed. We should be able to take that and use x sub c equals summation of a times x over the total area. So 165.8 over 70.43 equals 2.35. All right, let's check our diagram here and see if we're, that's not quite where I drew it. I drew it like 1.5, but I could believe it's at 2.5 also. So it kind of is, or 2.35. So it's really close to the centroid of the rectangle, at least in the x direction. Now we need the y direction. Okay, so we need all of the y values. All right, for part 1, I have that thing being 7 inches tall for the rectangle. So half of 7 is 3.5. I have the quarter circle here. Now, fortunately, the quarter circle y sub c is the same as x sub c. So, and the quarter circle, where y sub c is measured from, is the same place I'm measuring from. I have the x-axis right flush with the bottom of the quarter circle, and my reference chart, oh, I'm off the screen. My reference chart also has y sub c measured from the bottom of the quarter circle. So I can just use 4r over 3 pi. And it's positive because x-axis is at the bottom and I'm measuring upwards. I'm measuring, it's going to start to get cluttery. I'm measuring that distance right there. So 4r over 3 pi. 4, the radius is 3. Let's make it smaller than that. 4 radius, 4r over 3 pi. So it's just 4 over pi. Four divided by pi is 1.27. Okay. For the triangle, I need to start at the x-axis and measure up to there. So it's a positive value, and it is this distance, which is 4, plus that distance, which is, consult my chart here. So this one's a little bit tricky. So if I look at the picture, it shows me y sub c, and y sub c is 1/3 of the height. But if I look at my what I'm actually using, that's giving me this distance. That is 1/3 of the height. I need the other part of that. I need 2/3 of the height. So sometimes you have to mentally flip these things around, mirror them, rotate them even, to make sure you're actually using the correct equation. Don't just go blindly by, oh, triangle x y sub c is 1/3 of height. It is, no, that depends on where you're measuring from. So make sure that you look on the diagram, not just at the equation, but on the diagram, and see where are they measuring from, and is that where you're measuring from. So for us, the height of this was 3, so this distance is 2. I'm already 4 above the reference, so I'm actually measuring, the value is going to be 6. All right, and then a times y, I've got 2.5 for the area of the rectangle. Whoa, wait a minute. 91 for the area of the rectangle. 91 times y, 3.5. 318.5. A negative 7.07 for the quarter circle. A positive 1.27 for the y location of its centroid. So that's a negative 8.98. I'm having to round, to the hundreds places, so you might have slightly different numbers if you don't round. Triangle is a negative 13.5 area and a 6 centroid location, so that's 81, negative 81. And then I add 318.5 plus negative, so minus 8.98 plus another negative 81. 228, so the summation of a times y is 228.52. And then finally, y sub c is the summation of a times y over the total area, 228.52 over 70.43, 3.24. So that's reasonable. I put it at 3.5, so being a little lower. So basically it was really a little more like, I don't know, it was, what was that x coordinate? 2.35, so 2.35 and 3, so it's really somewhere right in there. That's really where it is. We were close on our guess, but that just is a reassuring thing that we're not doing anything crazy. It's still easy to get confused on some of these decimals or forget a negative sign somewhere. So you do have to be really careful. That's why the bookkeeping, all of this is probably the best way to start with. I saw a question on the steps for the triangles y again. All right, so it's getting really, I'm going to have to erase some of these because it's really cluttery up there. And we'll start over with the triangle. All right. So the triangle's y. First of all, I want to measure from the x-axis. I've kind of covered up the x-axis. It's there. That's the x-axis. And so I'm wanting to measure this, this line, this red line right here. want to measure that. So I know that this much of the distance is determined by kind of like where the corner of that triangle starts, and I can tell that that's 4 because I knew the total height was 7. The dotted line of the triangle is 3, so that leaves 4. So I know I'm at least 4. And then I've got to figure out, well, what is this distance right here? And I go to my little chart, and the triangle that they have, they've got a triangle turned this way. I've got a triangle turned this way. So it's a mirror image of the triangle that I'm using. And I want to know that distance. They're giving me this little distance. So they're giving me this distance. They tell me the equation for this one is over here, circled in green, h over 3. And so I just made I kind of reset it, and I said, well, that's 1/3 times h. And so if that's 1/3 times h, then whatever the leftover part is 2/3 times h. And that's what I need. I need that 2/3 times h. H is, shown on the diagram that it's kind of the height of the triangle. So for me, the height of the triangle is that distance is 3. So the 2/3 of 3 is 2. So that's where I got my 2 from. And then in my chart, I guess I didn't write it down, but the y triangle part is 4 plus 2 is 6. So those are all the little steps. You might have to replay that a couple of times. For some reason, triangles are the most confusing ones for most of the time. Second to these sectors over here. We don't run into these sectors very often, though, so I guess they're, this circular sector, we don't use that very often. But it seems to be a little more confusing than the triangles. But the triangles, flipping them, mirroring them, and figuring out where things are actually measured from can be a little bit tricky. Maybe it helps to take whatever the book is giving you or your reference sheet is giving you and then draw what you need and try to, match. Well, they gave me this. I actually need that distance. And the good thing about the triangles is that the centroid is 1/3 of the base or the height, which if you can think about it, it means that the centroid is closer to the fatter part of the triangle, like the right angle. It's not always a right angle, but the fatter part of the triangle. This particular one's a right angle, and that distance is going to be 1/3 from wherever your corner is. But there is another kind of triangle that they will use sometimes. This non-right angle type of triangle, and it's got a lot more dimensions you have to be aware of. But basically what they do is they turn it into a right triangle and then work from that point of view. I don't know that any of our problems ever use this particular kind of triangle in them. All right. That probably gives you plenty to work on. I'm going to open up the homework that's associated with centroids. It is in web work, so do be aware that web work and rounding don't always mix very well. So I would probably, I might even do this in Excel or something, so you don't have to round any of your numbers, because it is kind of like a Excel spreadsheet that I'm building. You don't have to build it that way. You can just build the equations directly. But as the parts get more and more complicated, there's more little pieces to keep track of. Might be good to have something like this to go back and look at to see if you left off a negative sign somewhere or something like that. All right. Oh, let's see. Could you... Geez, EX and... Oh, okay. This is something about homework. Homework 7, number 5. Let me look at that real quick. Homework 7, number 5. Now, my numbers are going to be different from yours, but, oh, this is a truss. So, let's see. First of all, what I would do with this one. You're asking particularly about GX and EX, so the reactions at those two pins. This one's a little weird. Normally you don't have two pins. Normally you have a pin and a roller. But if you look at G, there's only like a horizontal piece. So it only has GX. That's all it has. There's no GY. So you could, in order to solve the value for that one, what you would do is this. Let's drop this guy over here. So let's see if I can. We'll do that. I don't have an eraser for this kind of thing, but we'll pretend we're erasing this. Okay. So I would have, and again, I don't know which way they go, but I could put EX here and EY here, and I could put only GX here. There's no GY. So what I would do is I would do, for the external reactions, I would do summation of moments about E equals 0. You could do clockwise positive if you wanted to. And then you have your F1 times 2A plus 2B. Well, let's just write it. I assume you know all these values. Let's see. Yeah, you know F1, F2, 3, 4, A, B, and C. So you would have F1 times 2A plus 2B plus, oh, well, actually, that's minus. The way I said the moments are positive. So minus F2 times A plus 2B minus F3 times 2B minus F4 times B plus GX times C. Pretty much ran off the page there. Equals 0. And you know everything in that equation except for GX. And so you could solve for GX using that equation. And then you could just do summation of forces in Y equals 0. That will give you a value for EY. And then summation of forces in X equals 0 will give you a value for EX once you know the value for GX. So the key to that one is that there is no GY because of the way this one was drawn, where there's no member from E to G. So there can be no Y component to the forces at G because there's nothing in the Y direction. So that's kind of a tricky one. What's the exam going to be like next week? So the exam, let's talk about that for a second. Let me go to here. Yeah, home. Let's see what I've got in here. So the next class is the exam review. So questions from homeworks to solve. Let's see, what do I have in here? Going back over some of the stuff, doing some more centroid problems maybe, or truss problems. And then exam 1, if we look on that date, there is a outline. There's some reference materials. So basically the reference materials that you would need would be the centroid chart and maybe the material properties. There's a couple of practice exams, older practice exam problems. These are all, oh no, not all, mostly like 85% or so multiple choice questions. There are a couple that are context, like find all the zero force members in this truss, or what's the definition of stress, or something like that. There's a couple, maybe 10 or 15 points of that kind of thing, but most everything is calculation problems that are multiple choice. So you can check the exam. Well, it says 2023. That's going to be the same outline for 2024. So you can check that. You can look at old problems in these that say retired or this practice exam. You can look through those for examples of what types of problems might be on there. In general, they start at one-step problems, and there's maybe 50 points of one-step problems. So kind of like if you can know these kind of things, then you basically have a understanding of the very fundamental stuff. And then there's some 10, 20 points of two-step problems, and the remainder of three, not necessarily two-step, but harder problems that are multiple step, and then one or two that are relatively complex problems. They might take you 10, 15 minutes to solve one or two of those, just to see if you're A level or B level kind of grade. But you can look at these. These are in the class 10 on Canvas. You can look at those for examples of problems you can work through. It is timed, and I do we get on Zoom and you get on Canvas, and I will proctor at noon, and I will proctor again that same day at 7. So if you can't do the noon one and you could do the 7 o'clock one, then you pick one of those and you do one of them. You don't get both. You just pick one, you do one of them. If for some reason you can't do the exam on June 26th, then you have to arrange for a proctor, which you just send me an email and we'll figure out what in your case will work. Most of the time, most everybody can either do the noon or the 7 o'clock on the test day. But if you can't, then let me know so that we can arrange for however you're going to get the proctoring done. You can use calculator like regular. You can't use MathCAD. It's not open book. It's just these reference materials that are in these two folders here, 2 and 1. Just those are your references. You can print those out if you want to. So that's kind of the idea for all of the exams actually, but since this is the first one, that's kind of how it's going to work. You will, like when you're done with the exam, you'll take pictures of any scratch work that you used and upload that to this exam 1 work folder, just so I have your scratch work in case there's any questions to answer later. You plug those in there. Another question. I did not choose. So the question was, how did I choose these directions for GX and EX? I didn't. I just drew some arrows, and then I let the equations tell me that I choose the right direction for the arrows. So if I get a negative sign, I'm solving for GX and I get a negative sign, then I chose the wrong direction. If I solve for EX and I get a positive sign, I choose the right direction. So when you're drawing your own arrows, they're not like already drawn on the diagram, then you get to choose and just let the equations tell you if you chose right or not. So don't spend a whole lot of time trying to figure out if you're supposed to draw a reaction arrow left or right until you know, like you've solved an equation and it's told you that that should be going to the left or going to the right. But when you first draw it, just pick one. I usually pick the positive directions. I just pick GX going to the left because all of these F1, 2, 3, 4s are pushing down, which would want the truss to push into the wall, so the wall would have to push back. So I just instinctively drew it to the left. But if you drew it to the right, it'd be fine. Your equation, you'd solve this equation and it would say GX equals negative some number, and you'd just say, oh, that means my arrow was going the wrong way. Now you're saying in web work that the EX gave you the wrong direction. That is possible that web work has a problem. I haven't heard anybody else mention that. So I don't think so. It's probably something with your equation. You dropped a sign somewhere in your equation. Homework 5, problem 7. Let's see what that looks like. Homework, oh, this is homework 7. Homework 5, problem 7. Homework 5, 7, part C. Okay, so this is talking about axial deformation. I guess part C is the minimum wall thickness of the tube is the part C. Mine aren't labeled, but the third one is that. So what this is talking, let's see. Let's copy our diagram at least. Let's get this. Let's go over here and see what we've got in here. So I've got some materials, cast aluminum, hollow tube. I've got a rod with a certain modulus of elasticity. It has a nominal length, meaning the name of the length is 50 inches. Usually when you see something like nominal length, for us, that doesn't mean a whole lot. It just means use 50 inches. In the real world, it would mean like, hey, this thing, we call it 50 inches, like a 2x4. We call it a 2x4, but it's not actually 2 inches by 4 inches. It's 1.375 by, whatever. So nominal just means that we call it this thing, but it's really something else. But in this case, it's just 50 inches. Aluminum tube has same thing, nominal length, outside diameter. We've got a load on this thing. If the maximum distance the free end of the rod is allowed to be displaced, so we have a delta type of thing. Delta equals FL over EA. 0.03 inches, meaning it cannot move more than 0.03 inches downward. We figure out all this stuff. All right. So we've got this rigid plate on top, and it says rigid plate, and we don't have any information about it that I see. So what that will tell us is that it's not part of the problem. It's really only the tube and the rod are problems. The rigid plate is just drawn there to show that we're transferring force from the rod to the tube. Okay. So we want to find the change in length of the rod. So that's easy enough to start with. We have to do these kind of in order to do the third part. So the force on the rod for me is 33.11 kips. I'm going to put that in pounds just so my units are easier. Probably going to put this in MathCAD actually because of my calculator situation. L is the length of the rod. For me, 50 inches. Area is the cross-sectional area of the rod, which for me is 2-inch diameter. So pi 2 inches squared, pi d squared over 4. E for the rod, 24,000 KSI. So 24 times 10 to the 6 PSI. So those numbers would give me the change in length of the rod. And I do have MathCAD still open, so let's just figure out what that is. E was 24 million PSI. L was 50 inches. F was, I forgot, 33.11 kip. And A, whoops. A, what's the deal? A is equal to pi times, my diameter was 2 inches, pi d squared over 4, and then delta of the rod equals F times L over A times E. All right, 0.22 inches. All right. Well, I guess we can check that, can't we? Oops. Well, I have this option where I can actually check answers, and oh, all right. So see, here's a typical web work thing. The correct answer is 0219568. I put 022. That's fine on an exam or homework or anything, but web work is very particular. So if you run into that, well, MathCAD, you can go over to your math formatting and add more decimals. So do that first if you're using MathCAD and WebWork, because particularly with these small numbers like strain and changes in length, they're probably pretty small. Okay, now where's our problem statement? Now, the maximum change in length of the tube. Okay. Oh, okay. So remember, the rod itself has stretched 022, but I have that the end of the rod can't go down more than 03. So I lost my pen. So I've already stretched the rod a little bit. 0.022, even though WebWork doesn't like that. But I've got like this floor down here of I can't go more than 0.03 inches. So I've only got a little bit of room left that the tube can compress before I violate that constraint that I have. So delta of the tube equals 0.3 minus 0.22, and that's all it can do. And then equals the force. It's got the same force applied to it, so the F travels through the rod, through the rigid plate, and then gets applied as, a compressive force on the tube. So it's the same force, 33,110 pounds. The tube is, okay, so I don't know. All right, this is what the wall thickness is helping me solve. All right, so we're about ready to actually solve your question. So the area of the tube, mine outside is 5.5 inches. So before I forget, I'm going to write OD 5.5 inches. So the cross-sectional area of this tube is a donut shape. So the area is going to be, in my equation here, it's going to be pi times OD, which is 5.5 inches squared over 4, minus pi times ID, which I don't know, over 4. That's the area. And then times the modulus of elasticity for the tube is... does it not tell me that? Oh, all right. So I have to look it up. It says a cast aluminum 195 T6 hollow tube. All right. So I have to go over here to my, where did I put my material properties? Material properties. And I need to use the same unit. So I have two of these, right? I have one for metric units and one for the US units. And you can't translate between them. They're the same numbers, but these problems are set up for like exact things, particularly in web work. So 48 KSI for wrought iron is not exactly 330 megapascals for wrought iron. So there's some rounding that happens there. So since my problem is in inches, I need to use the US version of that. What was it? I forgot the number already. 195 T6. So it's this one right here, 195 T6, 10.3 million PSI. So 10.3 times 10 to the 6 PSI. So that would be the equation. All of this, I think it might have gone off the page a little bit. All of that's the equation, and there's only the ID, the internal diameter unknown. So I have to solve that equation for ID. And if I do that, I get, I'm going to cheat, I get 0.28. Oh, no, that's the wall thickness. So I don't actually know the ID. I get the internal diameter, and then the wall thickness equals the outer diameter of the tube minus the inner diameter of the tube divided by 2. Because, you know, if I look at the tube from the top, there's the outer diameter, and there's the inner diameter, and the wall thickness is that. That's the wall thickness. So that would be the process for solving that without actually having and, you know, doing the math to solve this equation. It's just a matter of finding out the ID, and, you know, realizing that you do know this is how much the rod has already stretched downward, and I've got some limit on how much further it can go. So that's if the tube compresses any more than this total amount, whatever this total is, then I've violated my constraint that's over here about this constraint here, the maximum distance that the free end, the tip of the rod, is allowed to move downwards. So that's a little bit of a word problem. You got to understand what's going on, plus a conceptual of, all right, so the rod is stretching, the tube is compressing, the rigid plate's not doing anything, transferring the force, I guess, and recognizing that the wall thickness is the outer diameter minus the inner diameter, but you actually have to divide that by 2, because if you just subtract, you know, if I just subtract this distance, or well, this inner one from that outer one, that's OD, that's ID, that would actually leave me with, you know, 2 wall thicknesses. So I have to divide that by 2 to get the wall thickness. Let's see. What's it? Yeah, so the comment about you can send the email of the actual work that you've done, that's probably helpful at that point, because it sounds like there's just some, maybe a rounding thing, or probably some sign convention that's off somehow. I'm not sure. But next time, no new topics. It's just review, go and practice, do some of the practice problems so you have an idea. And particularly if you're not going to be able to take the exam at noon or 7 on the exam day, I definitely need to know that so that we can arrange a proctor for some other time. All right, I will see y'all next time. I guess that's Thursday, that's tomorrow, at noon.